That's part of the reason we love complex numbers. What I just said is the fundamental theorem of algebra. Gauss proved that when he was about your age. But he was Gauss. So don't look at Gauss's accomplishments early in life. It's very depressing if you want to do math. Anyway, so there. Yeah. So if you turn the page here to page 44, I point out that this completing the square business straight away leads to the quadratic formula. All right, so see this? So if we have, you know, we have a times x plus b over 2a squared, right, minus b squared over 4a squared plus c over a, all of that try to use some square brackets here, right? If we look at that being set equal to 0, that straight away gives us that x plus b over 2a, quantity squared, must be equal to b squared over 4a squared minus c over a, right? And we could rewrite this as b squared minus 4ac divided by 2a quantity squared. See, because 4a squared is 2a quantity squared. So by algebra, it's that. And then you take the square root of both sides is one way to think about it. So we get x plus b over 2a is equal to plus or minus the square root of b squared minus 4ac over 2a squared. All right, and that gives me x is minus b over 2a plus or minus the square root, oh, sorry, let me keep the 2a downstairs here, minus b plus or minus the square root of b squared minus 4ac divided by 2a. And of course, this is the famous quadratic formula, right? The quantity b squared minus 4ac, what's that called? It's called the discriminant because it does what? It discriminates what kind of solution you have. If it's positive, you've got that case where you've got distinct real zeros, there's a real factorization. If it's 0, you're in the double root case. If the discriminant is negative, you're looking at a complex solution, right? If the discriminant is negative, your solution is minus b plus or minus the square root of a negative number. That means that the answer is complex, all right? Now, I have this all written out carefully, you know, at the top of my page 44 here. So, you know, comment. Complex solutions to real polynomial equations come in conjugate pairs. Conjugate pairs. You can already see this in the quadratic formula. When the discriminant's negative, we get a conjugate pair. Plus and minus the same imaginary piece. Here, let me point out another example of this. Now, see guys, we don't actually need the quadratic formula for examples if we complete the square, right? Like, check this, just return to this example here, before the example, this one here. If I look at this equal to 0, right? Yes, I could go back and I could say, well, a equals 1, b equals -6, c equals to -1. I could plug those numbers into the quadratic formula and find the solutions, right? Or I could use the factoring that we had done and say, aha, this equals to 0 gives me solutions x equals to, 3 plus or minus the square root of 10, right? So which is easier, completing the square and using the factor theorem to read solutions off, or like plugging numbers into the quadratic formula? I would argue completing the square and reading solutions from the factor theorem is actually faster and more reliable. I will just tell you, students have this proclivity of messing up this calculation when you're plugging numbers in a calculator. It's very rare to have students who are super competent in plugging numbers into this. Let's see here. This one, check this out. So if I said this equals to 0, what are the solutions? X equals to -2 plus or minus I root 2, right? This is one of those conjugate pair solutions I was talking about, all right? So let's look at in-class example 1.6.24. So here you're given, oh, by the way, I just left in-class example 1.6.22 for you guys to do. What was my agreement with you last class, guys? What did I say about in-class examples that I skipped and didn't do? What could you do with those? Right, now how do you get that extra credit? Am I clairvoyant? Am I all-seeing and all-knowing? No, so you actually got to write it out and hand it in to me at some point, Let's say by the first test, okay. Let's try to keep up to date with each test for those, yeah? So here's x to the 4th minus 4x cubed plus 6x squared minus 4x plus 5. All right. And I give you a gift that p of 2 plus I is equal to 0. All right? Now, what does that mean? Well, there's this thing, complex solutions come in conjugate pairs, right? So if p of 2 plus I is 0, it also has to be the fact that p of 2 minus I is also equal to 0, right? And that means that x minus 2 plus I and x minus 2 minus I is a factor. So both of these are factors of p of x. Now, if you look at that text box with the quadratic equation stuff, I in there show you that basically if you have p of alpha plus I beta equals to 0, that gives you that x minus alpha squared plus beta squared is factor. In other words, that's what is going to happen with that pair of conjugate factors. It's going to multiply out to that. Now this one here, if we multiply this out, we're going to get x minus 2 quantity squared plus 1. That's what this multiplies out to. It's easy to see if you just kind of rearrange the parentheses a little bit, But anyway, we're a little short on time, so I'm just going to get to it here. Now that multiplies out to x squared minus 4x plus 5. So if we can, all right, so we know that this is a factor of p of x. How are we going to factor p of x? Which strategy do you want to use from the start of today? Strategy 1 or strategy 2? I'm my own worst cameraman. May I suggest strategy 2 is the one to go with here, right? I mean, like I don't want to try to like guesstimate how to pull out. So let's try long division. Because I know you guys got other stuff to do today, right? So, do any of you have a class right after this?
I got a lab in about.
You had a lab. Where is it? Is it this building?
I think it's in Wallace.
Oh, curses. I'll write faster. X squared, x to the 4th minus 4x cubed plus 5x squared. So we take this and subtract it. These two guys cancel. We're left with x squared minus 4x. Well, wasn't that convenient? Plus 1. So actually, maybe this one we could have factored by grouping. Like it might have worked that way. See, because apparently, given this long division, we just figured out this can be factored as x squared minus 4x plus 5 times x squared plus 1. And that's it. And in terms of like factoring over the real numbers, that's completely factored. See, because the x squared minus 4x plus 5 is irreducible. You cannot break that down further over the reals, right? Because it's completing the square gave us that. And the x squared plus 1, well, that's also irreducible. So there you go. That's how we'd factor this quartic. Well, despite my best intentions, we're still not quite done with the algebra. So hopefully we'll wrap it up tomorrow in about another 20 minutes. Famous last words. And then we will definitely get to limits tomorrow. Hopefully it'll be sooner rather than later. And good news, that means your homework is not due tomorrow because I'm still not done with polynomials. And I have some problems in your homework that are about this. There's a problem which involves this like pairing. Like I give you the polynomial of, like 2 plus I is 0, and then I say to factor it. So that's kind of this is basically the idea is just this. If I tell you something like f of minus 1 plus 2i is equal to 0, that is a hint that x plus 1 squared plus 4 is factor. So that may or may not be something that was ever emphasized to you before. I suspect I'm teaching you guys that here. It's probably not something you saw before. So a complex 0 implies a quadratic factor. And the specifics of that, again, are on page... Oh, man. Where'd it go? $43. Nope. 44. And if theorem 1.6.21, I show you like how the complex thing multiplies out and what factor it gives you there. So anyway, please read the notes. If you guys got questions about anything, come ask me tomorrow or ask me in office hours today, whatever floats your boat. Thanks, guys.